All right, we're going to start again. Welcome back to the second day. It's not the last day yet. Huh? You still have work to do. So we're going to do again a 50-minute session and then have a break. And then have a second 50-minute session. So today I want to continue talking about basics of combustion, what I need to know and what you need to know to look at turbulent flames. So just to remind you what we said yesterday, we defined the stoichiometric ratio and we defined the equivalence ratio. So those are simple things. Since sometimes it's good to get prepared for things that you have to do on your own. That's a simple exercise that you can do if I tell you that you have a mixture, fuel and air, where I want the equivalence ratio to be equal to 5. Compute the fuel mass fraction, the oxygen mass fraction, and the nitrogen mass fraction. That's a simple exercise. I'm not going to let you do it. You can do it at home. The result is written here. If you want, in a mixture of air and fuel, to have an equivalence ratio equal to 5, knowing that the stoichiometric ratio is S, this is what the fuel mass fraction should be, YF. And so if you run the numbers in this thing, so that this is 28, this is 32. If you do it at stoichiometry, you use phi equal unity, and you look for different fuels at what the stoichiometric fuel mass fraction will be. This is what you find. So just to take one example, if we look at methane, which is the classical one, you see here that the fuel mass fraction in a mixture of air and methane, the fuel mass fraction, the methane mass fraction is 5%, 5.5%, which is really small. And that's an interesting property that we will use later. It really means that if you prepare a stoichiometric mixture of air and fuel, it is basically air. Fuel doesn't play a big role there in concentration, in composition. So for example, if you want to compute the density or the diffusion coefficients or the heat diffusivity, in many cases, we're going to be able to say, okay, it's the same thing than air. And that's going to be used a lot when we do theoretical approaches to simplify our problem. And that works really only when you have air. If you do an oxygen flame, that will be a different business. But it's a very useful property when you want to derive theories for combustion, so that you don't have to worry about this problem at least. So it really means that, if I come back to the examples I gave you here, when I told you here that the molecular weight is changing a lot, it is true in flames which are not using air. But in a premixed flame, if you have nitrogen, in the fresh gases, you have 80% nitrogen. In the burn gases, you have 79% nitrogen. So it's basically nitrogen everywhere. And so the molecular weight in an air flame is usually not far from constant. So that's a useful simplification. So okay, now I need to start going to CFD, and I want to focus on a few questions here. First, the first one is, what do we have to solve for in the combustion code? And how does this compare to classical aerodynamics? I know that many people in the room have probably been using softwares for flow computations, sometimes without combustion. Then when you go to combustion, there's a big question of what do you have to change? Now let's start by the beginning. If you compute the flow around an aircraft, I guess you know how many variables you're solving for. I hope you should know. And it's 5. Okay? At each point of the flow, you need to know the 3 velocities. You need to know the density, and you need to know the pressure or the temperature, because if you have pressure density, you have temperature, or enthalpy or entropy. Any of those variables are linked. So you need 5 variables if it's a compressible flow. Some of you may know that you can simplify these things. If you go to low Mach number formulation or to incompressible formulations, you will end up with only 4 variables. But let's say for the moment, we stick to the general framework of compressible flow, and that means we need 5 variables. Now, if you go to combustion, there's one thing here which is hidden, is the fact that since we were using air, and air, we said, is going to remain air all the time, we didn't have to solve for composition, but now we have to. What is composition? Composition is just a set of n values for the fuel mass fraction, the oxidizer mass fraction, and all the other species mass fractions. So it's n additional species. which really means n additional conservation equations. So now we have the same thing we had before, plus n additional species. In practice, by the way, you know that since the sum of all the species mass fractions must be equal to unity, you can say it's only n minus 1. Okay, if you have 1,000 species, it doesn't help much, okay? It's still a big job. So you see that, by the way, here, when we had 5 unknowns and 5 equations of conservation, here we jump to 5 plus n minus 1 unknown and 5 plus n minus 1 equations. And n can be large. Okay? You see that if you're talking about a 1D flame code with 300 species, so you go from a problem where you have to solve 5 equations to a problem where you have to solve 305 equations. That's going to be a big job. Now, what do we have to change on these equations? We discussed yesterday, the effect of species on turbulence, for example. So that we can see the answer to a problem like this by looking at these equations. So that's what I'm going to do. I'm going to look at these equations one by one and show you the differences with non-reacting flows. So let's start with the continuity equations. The continuity equations express the fact that the mass of species k, rho yk is also the partial density, rho k. So that's the density of species k. This thing changes like all other quantities because of convection by the velocity, but then you have 2 additional terms. One of them is the Vk here, which is called the diffusion velocity, and the other one is the omega dot k, which is the reaction rate. The omega dot k corresponds to chemistry, because if the species k disappears, for example, omega dot k will be negative. For the fuel, we expect this thing to be negative. It's going away. And Vk really corresponds to molecular diffusion. That's the fact that the species k can be transported by convection, but even in the absence of convection, because of molecular diffusion, because of shocks, the species k can progress. If you have a gradient of species mass fraction, then you will have transport. These 2 terms, of course, are new. They were not in classical aerodynamics, so we need a model for them. By the way, I must say that this is a place where, when you look at combustion codes, there are many ways to have problems. One of the things that you need to verify is that this is the conservation of one species. If you add all the species equation, you should find the conservation of the total mass, okay, which is just the sum of the others. So if you sum all this equation, you must have d rho dt plus divergence of rho u equals 0. That seems obvious, but you will see that in many codes, if you're not careful, it's not clear. So if you sum all these equations over k from 1 to n, you see then that the diffusion velocities must be such that sum of yk vki equals 0, and the sum of the reaction rates must be 0. This is normal. I mean, this we have all the time, because combustion, the way we do it, does not change mass. Okay, it conserves mass. When you write an equations like H2 plus 1/2 O2 goes to H2O, the mass of this is equal to the mass of that. So if you write your reaction rates in a consistent way, normally the sum of the reaction rates is always going to be 0. Now, how do you find the Vk? That's a more tricky question. The Vk, the diffusion velocities, can be obtained by kinetic theory, and the Vk don't come out by saying Vk equals something. If you really write the equations, you see that the Vk's are actually given by this equation, which is the gradient of the mole fraction of P is equal to that, Vk minus Vp, and there are additional terms here. This is a source term due to volume forces, so you can forget it. For those of you who would do effect of electric fields or magnetic fields, they would come in here. This is another term that usually we can forget. That's the diffusion due to pressure, and normally, in most combustion problems, we only have to solve this thing. But this thing is complicated because it's not an explicit expression for Vk, so it's actually what we call a matrix. Because if you want to write this thing in another way, you see that at each point of the flow, you're going to have to write diffusion velocity of species 1, of species 2, of species n. And here, you will have to put this term in front of each. So here you have a big matrix, M, And here you have gradient of x1, gradient of x2, and gradient of xn. And this is what we call the diffusion matrix. The diffusion matrix gathers all these terms here. Now, xp and xk are the mole fractions. dpk is the diffusion coefficient. That also comes from kinetic theory. It's the diffusion coefficient of species p into species k. dpk is equal to dkpk. You can invert them. That's fine. And it's given by collision integrals. Again, someone will give you the values of these things. You don't have to worry about them. What you have to worry about is that in a code, you don't want to do that. You don't want to invert this matrix at every point, at every time step. It's too much work. So what you can do, and here there's the reference book is this book by Giovangigli and Ern. Those guys are mathematicians. You have to, if you want to read this book, you get to get ready for it. I mean, it's tough. But what they show actually is that there are simplifications to this problem, what they call expansions with different orders of precision. And the first order of precision is this one, what we call the Hirschfelder's law, saying that the diffusion velocity Vk is linked to the gradient of the mole fractions divided by the mole fraction itself, with a coefficient in one of it, which is not dkp, it's dk. That's the coefficient diffusion, the diffusion coefficient of species k into the mixture. And so it's not equal to dkp. It's a bit more complicated. This one is the most precise you can have. Now, many of you, and many codes actually use this one, which is Fick's law. Fick's law is the same thing, except that instead of mole fraction, you have mass fractions. And you can show that in certain cases, this one works too. For example, if you have binary diffusion, only 2 species, but for combustion, 2 species, not much, because normally you need at least 3, but Fick's law would work. But in all other cases, really, the best one to use is Hirschfelder, and that's the one you find in codes. Now, depending on which code you use, if you take a look at the code, you will see that sometimes you will find a yk here, and sometimes you will find an xk. There are some differences between the two, because yk is not equal to xk. Okay? Yk, in general, is equal to xk multiplied by wk over w. And w, the mean molecular weight, is not a constant, so the two gradients don't have to be equal. So that's a first trick if you want to use these things. Now, there are a few other things you want to be aware of. So the binary diffusion coefficient, they come from kinetic gas theory, so they are tabulated. dgk equals something. You don't have to worry about them. But the problem is that this is not what you use in the Fick's law or in Hirschfelder's law. You use the decay. The decay is equal to this expression, 1 minus yk divided by a combination of all the djk in the mixture. And all the decays are, in general, different. And that's why we talked about the Lewis number yesterday. All species are diffusing differently. H2 atoms, for example, are diffusing very fast, and the H atom is probably the fastest one. It's diffusing typically 6 times faster than a big molecule. Now, the interesting thing is that the decay in a mixture, they change a lot, but their ratio, if you normalize it by the diffusion of heat, this ratio does not change, almost. So that's an example here. We took a laminar flame, so that's a laminar premix flame. So you have the fresh gases, the burned gases, and this is the diffusion coefficient of the heat normalized by the diffusion coefficient of species K, so that's the Lewis number, plotted as a function of position. And you see that those things are almost constant. They change a little bit in the flame, but it's almost the same. So it tells you, for example, that CH4 has a diffusion coefficient, a Lewis number, almost equal to unity. So when you have methane in the flame, it's diffusing almost like heat. Lewis number equal unity. But if you look at H2, of course, H2 has a diffusion coefficient which is much less than 1, which really means that the diffusion coefficient of species K is very large. And as we said yesterday, it's because it's a small molecule, so it's easier for her to travel in the system. And of course, if you take big molecules, it's the other way. CO2 is big, so it will have a Lewis number larger than unity. Now, many of us want to include this effect of Lewis numbers in their codes. That means they want to be able to say that the Lewis number of all species are different. The trick is when you do that is you still want to enforce total mass conservation. And that's not always the case. So for example, if you look at this equation here and you sum it, then you see that instead of having 0 on the right-hand side, if you have used Hirschfelder's formulation, for example, you have this expression, which is not 0. So as soon as you replace, the big jump has been done here, as soon as you replace this expression by this one, you don't necessarily enforce mass conservation. You have to do something about it, otherwise you will lose mass or create mass. So how do you do that? Well, the usual methods to do, there are different ways to do that. I know that a lot of people compute n-1 species, and then the final species, they say it's 1 minus the others, and then of course you don't have a problem. But if you look at what this last species is doing, it has a very strange behavior. The best recommendation here, again, and that's in the book of Giovogigli and Ern, is to replace this expression by this one, where here you add a correction velocity. And this correction velocity is there to satisfy mass conservation. So you replace this expression by that one, and you choose VC, so that when you sum this thing, the velocity of correction here balances this term here, which is due to the approximation, due to the Hirschfelder formulation. So you write VC equal that at each point, each time step, so that you conserve mass. If you don't do that, and many codes actually don't do it, many codes only use this expression, then you don't conserve mass. That's as simple as that. And if you don't check it, you don't know it, but one day you will find out that there is a problem. So you want to be very careful when you start using a code, or if you write your own code, don't write VK equal this, because that does not conserve mass. You need to add this correction here, which is the correction velocity. Now, let's jump to the momentum equations. That's the equations you write when you want to solve for the velocities. Here, there's no surprise. The equation for momentum is the same with and without flame. Like I said yesterday, the velocity field does not care about species. The velocity field cares only about density and pressure gradient, and of course viscosity. Now, does that mean that combustion does not play any role here? No, because the viscosity tensor has viscosities here, and these viscosities change when there is combustion, because viscosity typically changes like the temperature. Temperature increases, viscosity increases. Okay. Which really means that nu, which is mu over rho, increases like t squared, because this goes up like t and this goes up like 1 over t. So that's actually a surprising result. Well, not surprising, but that's the way it is. That's the viscosity, the kinematic viscosity of the burned gases is much more than the kinematic viscosity of the fresh gases. In a factor of, if the temperature goes up, if you go from 300 K in the fresh gases to 2100 in the burned gases, temperature has been going up by 7. That means that nu has increased by 49. So the burned gases are much more viscous than the fresh gases. Except you don't have this feeling, because when you look at a flame, your eyes are dominated by buoyancy effects. You see the burned gases going up because they are lighter than the fresh gases. That does not mean that they are not more viscous. Okay, they are actually more viscous. There are examples, I think in the book of Lewis and von Elbe, there's an example of a jet which is turbulent when it's cold, and when you ignite it, it becomes laminar because it's more viscous. So there is an effect of flames on the field of velocity, but it's only through the fact that density is changing and viscosity is changing. So if you have a code which solves for classical aerodynamics, you don't change anything here. You just add here a mu which is changing with temperature. Okay, now, of course, the last one is always the best one. Here, it's the energy. The energy is where things get more interesting. In practice, Please?
What should be the model that we should use for mu?
For the viscosity, there are different, okay, for mu, depends how precise you want to be. If you want to be very precise, there are models which gives you mu as a function of the yk and the mu k, the viscosity of each species. But in practice, what we do is the following. We just use a correlation. For example, if you're using air, the Sutherland formula works really well for air. It's a correlation as a function of T. Well, there are different ways. Normally, you can write it this way. Or if you want to use Sutherland, it's a bit more complicated. There's a 1 plus T something, or it's 2 power here, but that's about the same. And honestly, when you use this complicated formula, if you do an air flame, that's quite sufficient. Sutherland is really good to do that. Now, that's a good test, actually. If in this room, many of you are using combustion codes, if I ask you which equation of energy you're using, I'm sure you're going to have a difficult time to answer. Because each code is actually using a different energy. So it can be energy, it can be enthalpy, it can be temperature, it can be a mixture of these guys. So, and of course, all these equations for energy should be equivalent. And when I wrote the first version of my book, I said, okay, it must be simple. So I started from one and I derived all the others. It took me a long time. So, so the trick is, as you will see in a second, there are many equations. That's fine. But you want to know which one you're using, and you want to avoid mixing these equations because they look the same, but they are not the same in practice. There are other issues here. I'm going to talk only about compressible equations. Be careful of incompressible formulations for energy because strange things may happen there. If we stick to compressible, the question is to see which quantity you're solving for. So this is summarized again in the book here. And you've seen yesterday, we started discussing that. By the way, we need to define energies and enthalpies with combustion. That really means that we're going to talk about molar quantities or about mass quantities. And the two are linked simply by the molecular weights. And unfortunately, as I said yesterday, not only do people use different energies, but also they use different quantities. Some codes work with molar quantities, typically 0D, 1D code, and most 3D codes, they work with mass quantities. So yesterday we wrote this already. The enthalpy of species K has two parts, the formation enthalpy and the sensible enthalpy, which really measures temperature. And these things are usually tabulated in your code. This quantity is just one set of data, and this one you've seen yesterday, for example, for the NASA polynomials, this is tabulated as a function of temperature. So again, for you, it's not a problem. You can just pick up the tabulation. And once you have this, you know that the mixture enthalpy will be the sum of the yk, hk. That's reasonably simple. The formation enthalpies you get from tables. And again, you be careful here. Use only international units. So if you talk about the weight, it has to be in kilograms. And here you need to talk about the mass formation enthalpy or the molar formation enthalpy. And as I said yesterday, all these things are zero by convention at the reference temperature. There's a small trick here in the literature also, is that there are in fact two reference temperatures. One of them is 0 Kelvin. The second one is 298.15. So you want to be careful also when you write a combustion code to decide if you want to work at 0 Kelvin or 298. It's the same, but you don't want to mix the two quantities. So yesterday also I started discussing this question of the CPs now, the enthalpies. Remember that if you do only airflow, the molar quantities are 3.5 R for the CP and 2.5 R for the CV, where R is 8.31. And which really means that this is only for air. If you want to do a flame, that does not work. This is here temperature. And here you have the perfect gas limit for diatomic gases. And sure enough, all the diatomic gases go to 3.5. If you plot here Cp over R, that's the perfect gas limit. But when temperature increases, then that's not the case anymore. And of course, certain gases are not diatomic. And you see CO2 or H2O. And so even if they are diatomic, the Cp goes up with temperature, and that's something which is difficult to neglect. So in certain codes we will, When we do COE, we will also, but if you want something precise, I'll come back to that in a second, you cannot do that. So that's for molar quantities, CPK-M. If you do the same thing for the mass capacities, you see here for the mass capacities the variations, and you can see that it's changing a lot. Okay, for water or CO2, the changes are very large. You cannot neglect them. Now, an interesting question, especially when you write a code, is to say, do we really have to care about that? Can we just not say that Cp equal constant? What are we going to lose? Well, in most codes, you cannot do that. If you want a real temperature, you cannot do that. You have to account for Cp variations. But in theory, when you're writing theoretical formulation, usually you don't. You just say Cp equal constant. It's already complicated enough. You will see in 5 minutes how complicated it can be, so you don't need to account for variable Cp when you do analytical derivations. What does it really mean? What happens if you assume constant Cp? Well, if you do an air flame, and we've seen actually an example yesterday, the adiabatic flame temperature are usually over-predicted or under-predicted depending on which Cp value you take. Because if you say Cp is constant, you still have to say which one you take. Do you take the low value or the high value? Well, if you take the middle, you get a reasonable approximation, but you have to expect errors of the order of a few hundred K, which is, not that bad. The problem is really that if you want, for example, to predict pollutants, then you're stuck. Because you know that NOx formation is extremely sensitive to temperature. When you increase the temperature in the burn gases by 25 K, you increase the NOx by a factor of 2. So if you are wrong by 200 K, then the NOx can be wrong by 1,000. So then you're dead. You cannot do that. So if you want to look at pollution, then you need to account for Cp variations, otherwise it's not going to change. Now, the rest of the physics is unchanged. So you can still, there are many people doing very good work in combustion, saying that Cp is constant. You just have to avoid doing it if you want to do pollution. That's not going to work. So I'm going to jump that. And so go back to my CFD business. I have derived the equations for density, for the velocities, and for the partial density of the species. I need to talk about energy. Now, for energy, the question is, first, which variables you want to solve for? You know that if you write a code for classical aerodynamics, you work normally with total enthalpy, which is the enthalpy plus the kinetic energy. Now, in combustion, it's a bit more complicated because you have many energy, or many enthalpies. If you start with the sensible enthalpy, which has only the temperature in, you can add then what we call a total enthalpy, where you do the same thing, but you add the formation enthalpies if you have reaction. And then you can also add the kinetic energy. And so the total enthalpy, which includes all that, is actually getting more complicated because you can combine things in many ways. So that means that you have at least 8 different forms of equations for energy. You can write equations for energy or equations for enthalpy, and you can write them only for the sensible part, or you can include the chemical part, and you can add the total energy, adding the kinetic energy. Now, you can derive all of them. And usually a good starting point is to begin with ET, which is ET is here. It's the total chemical energy. So for this equation, the conservation is actually simple. It's a conservation equation for ET here. There's a source term here. There's a flux here, which is the heat flux. And there's a term here, which is the power of the viscous tensor. And that's all there is here. There's a small detail. The heat flux here, it's not minus lambda grad T, which many of you probably know if you've done heat transfer. You need to add this term here, which is the flux of enthalpy due to molecular diffusion. If there is molecular diffusion, each species carries its own H that creates an additional flux that must be included in this thing. But it's not a big deal, okay? If you start from this equation and you use these relations between all the expression, you can derive all the energy equations. It's an awful game, okay? You got many of them. Just make sure that you're using the right one in your code. There are tricks here. For example, many students come to me and ask questions about, you see this one, for example, here there's a gradient of sigma u, and here there's a sigma grad u. That doesn't mean that sigma is constant, okay? It just means that in this case, it's the total energy. In that case, you have removed the kinetic energy, and that's why the sigma goes out of the parenthesis. Now, if you're using a code using this quantity, just make sure that no one got it wrong here. And it's the same for all equations. And in your code, it's a good idea to verify that you know exactly which equations you're looking at. Now, in most codes also, these volume sources are 0, except, again, if you're doing funny things with magnetic fields or electric fields. And the volume forces also are 0. So that simplifies a little bit the equations. So let's go talk about heat release now. In each specious equation, you have a reaction rate omega dot k. All these omega dot k are combined to create the heat release now, which is omega dot t, and it's a combination of the formation enthalpies and the heat release, not the heat release, the reaction rate of individual species. So there are n reaction rates like this, and there's only one heat release. There's one equation that people like to work because I guess it's simpler to use and more intuitive. It's to look at the temperature. Just by the way, the notation here, this big D is the total derivative. That's a convenient way if you need to work this equation on these equations. D over dt is d over dt plus ui dxy. So this is the derivative of something which is carried by the flow. We call it also the Lagrangian derivative. So this quantity, if you derive it from the previous equations, then you start seeing here the heat release, and you have the gradient of temperature, and you have an additional term here, which is a little bit painful. Okay, it's what it is. It's due to the diffusion velocities. Now, this heat release is a small problem because this is the energy equation. There is one heat release here, and this is the temperature equation. There's another one, and they are not equal, unfortunately. The first heat release, which is here, is this expression. The second one, which is the temperature equation, is almost the same thing. You see this term here is also here, but there's an additional term including HSK, which is the sensible enthalpy. So that I'm just mentioning that because a few years ago, one of my students spent almost 2 months comparing his heat release with the heat release of another code, except he was not comparing the same thing. In the literature, people will tell you, this is heat release, but they don't tell you which one it is. Actually, we should have two words, two separate words. One to say, this is the heat release of the energy, this is the heat release of the temperature. And of course, there was a mismatch between the two because he was not comparing the right expression. He was missing this term. And when we included it after 2 months, then it worked. So you need to know, again, which equation you're solving if you want to compare to someone else, for example. Now, there are simplifications. One of the useful simplifications is to say that the CPs are equal. And when we're going to do COE, that's what we're going to say. If the CPs are equal, then all the sensible enthalpies of species are equal to the same thing. And when you sum this term here, HSK omega dot k, it's 0, which really means in that case that the two heat release for pressure, for temperature or for energy are the same. But that's a specific case, okay? It's true only if all the CPs are equal. Now there's a second simplification. If all the CPs are equal, you can get them out of this term, and then what's left here is 0, and you end up with the temperature equation that many of you probably have seen. This term goes away, and you end up with rho Cp dt dt equal heat release plus heat flux, okay? And that's the equation that people expect, you know? Temperature is changing in a flame because of two things: temperature gradient and heat release. And we're going to use this equation quite a lot because it's simple enough to do theory. So now, if you look at the equations I've written, we could stop here, any combustion course, and tell people, okay, you have the equations, I just have to go ahead and solve them, and that's the end of the course, okay? In practice, if you try to do that, it won't work. Okay, if you take the Navier-Stokes equations for combustion, you code them, you use any flame, and then nothing works. So if you want to understand now what the code is doing, you need to do it yourself. not let the code do it. You need to go and run a few cases. We call them canonical cases. Canonical cases are cases where you can not only run the code, but also write some theory and understand what you're doing. And that's really mandatory for combustion. There are fields, if you want to compute structural mechanics, the stresses in this table, you can use a commercial code. You don't need to understand anything. You just plug everything in the code and you get the result. That doesn't work for CFD of combustion. A lot of people in companies would like CFD to be here, you know. That's the dream of many companies. So probably most of you know CATIA. You know, it's a CAD system. So in CATIA, you would design your combustor, and then here there will be a very small button, and you would click on it and say compute, and poof, you would get the result, okay? That's not going to happen, never, because for turbulent combustion, there's just no way it can be done. It's just much more complicated. I know that people would like this to be true, but it's just not true. So I'm going to have now to go into these simple examples and show you what we learned from them. The first one will be the premixed laminar flame. We talked about it already. It's a useful animal to study because it contains all the ingredients of combustion. We'll be able to derive what the flame speed is, what the flame thickness is, and to give all the scalings related to laminar flames. And then we talk about the laminar diffusion flame too. So the premixed flames. There are cases like this one, you can solve completely the equations for a premixed flame. I've said that yesterday. If you assume that you have to have a planar flame, a 1D flame, moving at a constant speed, you can sit yourself on the reference frame of the flame, and this becomes a steady problem, a 1D steady problem. So instead of x, y, z, t, you only have x. That's good, better. Now, the problem is, even if you do that, you still have to solve the problem. Huh? You still have to write a few equations. So what do we expect? We expect to see a structure like this one. Here, the fresh gases are cold. They are entering the domain. Then they burn. Here is the reaction rate. Okay? And here is the fuel mass fraction. So there will be a lot of fuel in front of the flame. It burns through the flame, and there is zero fuel left on the right-hand side because we're going to look at lean flames. So flames where there is no fuel left in the burned gases. The question is, can you solve this by hand? Well, if you simplify the Navier-Stokes equations for that case, you see that it's still a complicated set of equations. The density equation is simple now. We know that the mass flux everywhere in this 1D flame must be constant. So it's rho u at every point must be equal to the inlet value rho 1, u1. And U1 is equal to SL. As I said yesterday, if you're on the reference frame of the flame, the flow is coming towards you at the flame speed. Now, the specious equations are going to be simpler somehow. There's no unsteady term, but still, we have to solve for velocities and heat release, reaction rate, and the temperature equation is what it is. Okay? So you can put that in many codes, even if you have a complex chemical scheme, and all these codes here will do the job. Not always in 2 minutes, okay? It can take a while to make them converge. And you will get this kind of results. That's an example for an H2O2 flame, so that's a very extreme flame. You have here all the profiles of species. You can look also at the thickness of the flame. You see right away that from here to here, there are 0.2 centimeters. So here the flame thickness must be a few hundred microns maybe. And you see that temperature is evolving slowly, actually, compared to other species. You have here intermediate species like H2O2, which appear only in the flame and disappear right away. So there is no H2O2 on any side, but in the middle, there's a big peak of H2O2, and you need to capture it. The problem is that this still needs running a code. So it doesn't tell you much about the physics. So can we do better than that? Well, you can do better. You will have to use additional assumptions. If you want to do mathematics, this is what people did 100 years ago. There was no computer anyway, so people had to find a way to use, their brains instead of the computers. So how did they do that? Well, the first thing is to say, okay, suppose you have a single reaction in a lean flame. So it's only fuel plus oxidizer goes to product. And the rate of reaction, we're going to write like this. We're going to say it's a constant, the pre-exponential constant, multiplied by y fuel, yo exponential minus TA over t. And that's a very reasonable expression in a premix flame. Now, if we say that the flame is lean, it really means that we have a lot of oxygen there. We have a lot of oxygen in the fresh gases, a lot of oxygen in the burn gases. So we might as well say that the oxygen mass fraction is constant. It's not going to play any role. What's going to be important is YF. So we just gather these two terms together, we say it's a constant, and we end up with a reaction rate written only as a function of the fuel mass fraction. Oxygen, there is plenty of oxygen anyway. Which really means that now instead of tracking all mass fractions, we only need to track the fuel mass fraction. So that's good. We had n equations, now we have only one equation for the species. So that's one major simplification. So now if we go back to our set of equations, this is what we have. We have the continuity, we have the fuel mass fraction, we have the temperature. That's still a lot of equations to solve, okay? Those are differential equations, second order. If you want to solve that, it's not going to be that simple. Note that here, if there's only one reaction, the heat release here is directly related to this one by this relation. This is the heat of the reaction. So if you burn 1 kilogram of fuel, you create Q joules in the temperature equation, which makes sense if you have a simple equation. And note that this guy is negative, so that this one is positive. Okay? You burn fuel, you create heat. That makes sense. Now, a lot of people have worked on this equation. They love this equation. The mathematicians, they love working on this field. And I'm just going to give you a small view of how you do this business. The first thing you can do, which is interesting here, is to integrate this equation from minus infinity to plus infinity. That's an easy exercise. That we're going to do it here. If you take the first equation, for example, this one, and you say you integrate it from minus infinity to plus infinity, you see that a lot of things are going to be simplified. The second term here becomes equal to this, minus infinity to plus infinity, and the third one is the integral of omega dot f dx. So those terms are very simple interpretations. This thing here is the gradient of fuel at infinity, which is 0, and the gradient of fuel at minus infinity, which is 0 also, because the fuel mass fraction looks like this. No gradient here, no gradient there, so this is 0 minus 0, that's easy. This is what we will call the total reaction rate, omega dot f. It tells you everything which is burnt in the flame. And here, this one here, is actually ρ1 SL, which is a constant, multiplied by 0 on that side, minus the fuel at the inlet. So when you integrate this equation, you find that ρ SL YF1 is equal to minus this term here, the total consumption rate. You do the same thing for temperature, and you find that ρ SL CP, T2 minus T1, which is the temperature elevation in the flame, equal minus Q multiplied by this term here. Now, these two equations have very simple interpretations. The first one is written here, and that's an important one. What is this thing? If you look at it, this is the flux of fuel entering the domain. Okay, this is a total flux, ρu. You multiply it by the fuel mass fraction, you have the flux of fuel. That's the amount in kilograms per second and square meters here entering the flame. What does this fuel do? Well, this fuel has no choice. It's burning in the flame. Okay? So this equation is telling you that all the fuel entering the flame is burned in the flame. Then when it's burnt, what does it do? If it is burnt, it will create a heat, which is minus Q multiplied by that, and this heat will be converted into temperature. And so this equation has a very simple interpretation here. We can eliminate the reaction rate here and obtain Cp T2 minus T1 equal Q YF1. So that's the heat release due to combustion, and that's the temperature elevation in the flame. And this is what explains that the temperature goes up from here to there, while the fuel mass fraction goes the other way. There's another interpretation that you can keep in mind. Here's the following. This is the fuel entering the flame, the fuel flow rate. This fuel flow rate goes into combustion. This combustion creates heat. This heat comes back and leads to temperature elevation. That's really what a premix flame is doing. Now, if you want to solve that, for the moment, I haven't done much. Just by integral properties here doesn't mean that we can have a solution. We need to do more. So to do that, again, like yesterday, like a good mathematician, you start introducing reduced variables. So for example, you scale the inlet fuel mass fraction. Here, every fuel mass fraction is scaled by its inlet value. So this guy will go from 1 in the cold gases to 0 in the burnt gases. And for the temperature, you do it the other way. You scale it by the temperature elevation. So it's T minus T1 divided by T2 minus T1. So the reduced temperature, and this is a quantity we'll use all the time for premixed turbulent flames, goes from 0 in the cold gases to 1 in the hot gases. Okay? Now, it's still a lot of equations to solve, even if you do the change of variable. So the thing we do is that we create the equation for y and for theta, and we add them. And we see that when you add these two equations, after scaling them, you end up with an equation for y plus theta, which has no source term on the right-hand side. So that's a very specific equation. You know that in combustion, our main problems come from reaction terms, from these source terms here. So every time we find an equation which has no source term, we're very happy about it. And we call it a passive scalar. Okay, we'll see that again today. And passive scalars are very convenient quantities because we can solve for these equations. Actually, this one is extremely easy to solve for. Why is it easy? Well, you know y plus theta as this conservation equation. And what are the boundary conditions for y plus theta? Well, it's 1 here. It's the sum of these two in the fresh gases. And it's 1 also in the burnt gases. So what is the solution of this equation with this boundary condition? Well, this equation is an equation of the type y prime equal a y double prime, okay? And we know that the solutions to that are exponentials. What is the exponential which goes from 1 to 1? Well, there's only one. It's 1, okay? The only solution to this problem is y plus theta equal 1 everywhere. And that really tells us something. It tells us that for this case, where we assume Lewis equal unity, I forgot to tell you that while here, to be able to combine these two equations, I had to use the simple approximation saying that ρd is equal to lambda over Cp. So if Lewis equal unity, you don't have two independent variables in the flame, you have only one. You can work with the fuel mass fraction, or you can work with the temperature, but this is the same variable. You don't have to worry about, solving for the two. You can use only one. There's a simple interpretation to that. It's that it really means that the chemical enthalpy plus the sensible enthalpy are constant. Either you are cold and you have some fresh gases, or you are hot and you have burnt all your reactants, all the fuel. And so this is a useful quantity because now it means that everywhere we can drop one of these two and keep only one quantity. What is done in the premixed flames community usually is to stick to theta because it's the reduced temperature. So what you do is you keep the equation for the temperature, and then the heat release here, everything which has y, you replace by 1 minus theta. So it's this term. This is the fuel mass fraction. You know that now it's not the fuel mass fraction anymore. It's 1 minus the temperature. And now if you look at this equation, you are getting one step closer to being able to solve it because it's one single differential equation where there is one single unknown, which is temperature. This is constant. This is constant. This is the temperature. This is a constant. Here you have temperature. So it's a single, simple, well, it's not simple yet because the shape, of course, the form of this guy is not simple. But still, it's a good starting point. So at that point, what most people do is to say that this expression, the beta here, is 0 so that there is no dependence on the temperature here to keep only the two other terms. The reaction term on the right-hand side becomes this expression. It's a constant, the density, but the density is also a function of the temperature and this exponential. So that's the final expression for the heat release. Now this equation has been fascinating mathematicians for a while because they were saying, okay, what can we do with this expression? This expression has actually interesting properties. If you plot the reaction term as a function of the reduced temperature, and again, you'll see that when we go to turbulent flames, it makes a big difference, actually. This thing is really characterized by the stiffness of this term. As we said yesterday, for low temperatures, nothing burns. For intermediate temperatures, nothing burns. And when you reach high temperatures, then suddenly everything burns. And the maximum of the heat release takes place here, very close to 1. How do we know that? Well, you can derive these expressions here. If you try to look for the maximum value of omega dot t, it's a good exercise too if you want to do it tonight. You take the derivative of this guy and look for the moment where it is maximum. It takes half a page. And you find that it is maximum at a value which is 1 minus 1 over alpha plus beta. Alpha plus beta are also the classical numbers which everyone is using in that field. Alpha is T2 minus T1 divided by T2, and beta is alpha multiplied by the activation temperature divided by T2. Alpha is of the order of 0.9 normally, because T2 is large compared to T1, and beta is a large number because the activation temperature is large usually. So everything I'm doing here is like a crash course to what we call asymptotic theory, large energies of activation, and where we're going to use this property to simplify the problem. Because beta is large, the shape of this curve becomes what it is now, and that's a property that we will use now to solve for the flame front. How do you do that? Well, since you see that there are basically 2 zones in this flame, you split it in 2. You say, when temperatures are low in the flame, nothing happening in terms of reaction rate. So we'll call it the preheating zone, and in this zone, we don't have to worry about combustion. There's only convection and diffusion. And then, if you're close enough to this value here, then suddenly you have combustion, and you have what we will call the reaction zone. So if we go back to our flame here, it really means that in a premixed flame, we expect 2 zones. Here there will be a preheating zone, and here there will be a reaction zone. So that's a useful information, and we'll use it for the solution. So what we're going to do is to find an expression now using these methods to find the flame speed. How do you do that? I'll do it after the break. I'll just give you the flavor of how we do it. I'm sure most of you are familiar with boundary layer theories. You know, you use boundary layer theories to compute the drag on an aircraft, for example, by solving the equations far away from the wing, and then here, in the boundary layer, you solve different equations, and then you connect the 2. We're going to do the same thing. We're going to solve equations in this zone from here to there. Then we're going to solve equation in this zone, and then we're going to match them. That's the method of asymptotic expansion, matching expansions here. And this is what you use for flames. So I'm going to do that. Actually, you can do it for this expression. For the full expression here, that takes a few pages. I'm going to do it using a simpler model, which can be entirely derived by hand. And we'll do that after the break. So we take 10 minutes break, and we come back in 10 minutes. If you have questions, you can ask them now or during the break if you want. So let's do some analytical work for a minute. So what I'm going to do now is to use this property here, saying that the maximum zone where heat release takes place is around theta equal 1 minus 1 over beta. And beta is a large number. Beta is of the order 10, so it's typically 0.9. So that what that really means is that in a flame like this one, nothing really burns before you reach this zone. Okay? So everything which is cold does not react. No way, cannot burn. So I'm going to use that, and that's something we did a long time ago with one of a postdoc who was working with, at the same time I was working at Stanford, and this guy had a big quality. He was very lazy. So he told me, I'm not going to do it with exponentials. I want to find a simpler model. And he found actually an elegant way to get the result in a few lines. That's what I'm going to do now. He said, what is important about the physics of this problem is not the exponential shape here. It's the fact that nothing burns and then everything burns. So let us replace this exponential shape for the heat release by a straight line up to this point and then a straight line here. Why did he use straight lines? Well, because we know that if you have a linear expression in a differential equation, we're going to be able to find the solution. While we know also that if we do it with an exponential, it's much more painful. So he said, let's replace this expression by another one, which says reaction rate equals 0 down to this point, reaction rate equal a line after that point. So these two expressions are actually simple to code. So we'll still have a preheating zone with no heat release, and then we'll have a reaction zone here where we have a linear heat release. And that's sufficient to solve the problem. So let me show you how. The first thing you do is you start working in the preheating zone. The preheating zone is from here to this point, 1 minus 1 over beta. And in that case, we know there is no heat release. So the equation looks like this. Convection equals diffusion plus 0. And the boundary conditions are simple. It's temperature equals 0 here, and temperature equal 1 minus over beta at that point. So you plug that into this expression, and this is a simple differential equation, okay? It's y prime equal ay second. We say for the moment that lambda over Cp is constant, and you integrate this thing, and this is the expression you find. So you right away, you see that with this very simple theory, you see that temperature is changing like exponential x over delta, where delta is something I will keep for later. Delta is the diffusivity in the fresh gases divided by the flame speed. So this is already a flame thickness. Okay, this is typically something which defines the thickness of the front. So if you want to do CFD later, it's a useful information because it tells you that that's a good quantification of the thickness that you need to resolve. Now, once you've done that, you can do the same thing now in the reaction zone. Since you say that the reaction rate is a linear function, you can write it like this. 1 minus theta, that really goes from this point here to 0 at that point. Theta equal 1 gives you 0. And here you have the maximum heat release at that point. And R plays the same role as a pre-exponential constant. When R is big, it's a lot of reaction. When R is small, it's a slow flame. So how do you integrate this thing? When you know the boundary conditions. Now, if we go at the flame, we must have theta critical. And if we go far away in the burn gases here, theta must go to unity. Okay, here we got 1. And here we got 1 minus 1 over beta. So you integrate this thing. It's not that difficult. You just have to assume, because you know it's a linear equation now. In a linear equation, we know that the solution will be written as an exponential. So you say exponential gamma x, you plug it into the previous expression, and you find a second order equation in gamma, which you solve, and it gives you gamma right away. And so the solution in the reaction zone now is written like this: 1 minus 1 over beta exponential gamma x, where gamma is this expression. Very simple one. And so at that point, you can say, okay, we have everything. We have the variations of temperature up to that point, and then we have the variation into this zone here. That's the exponential x over delta, and that's the exponential gamma x in this zone. And you could say that with these expressions, the problem is completely solved. Except that someone like this nice guy here told me, well, I don't have a cell, okay? I don't have the flame speed. In all this expression, which is fully analytic, I need the flame speed. I know the diffusivity of heat in the fresh gases. That's easy. And, but flame speed I don't have. How do I get the flame speed? Well, the flame speed is unknown at the moment. And this is where you need to do something. You need to do the same thing you do for asymptotic methods. You need to match here the equations, because what I've done here is to say that temperature was continuous, but the heat flux is not continuous at the moment. In other words, if you plot these solutions for this problem for different values of SL, and this is 1 minus 1 over beta, this is what you will get if you don't get SL right. Or you will get, something which is going up too fast. But the flux here will be continuous only if the flame speed has the right value. And this is how we're going to find the flame speed. To find the flame speed, now what we need to do is to say that at the place of the flame, the heat flux is continuous. So we need to write that the derivative of temperature on the left side of the flame is equal to the derivative of temperature on the right-hand side. And when you do that, you find an expression for SL, which is written here. And this expression for SL now is completely closed. SL is 1 over beta multiplied by beta minus 1 here. And this is the product of the diffusivity by the pre-exponential constant to the power 1/2. And when you have that, now you really have everything, because you have here the analytical expressions everywhere, and all the coefficients here are known now because you know SL. And so you can completely by hand solve the expressions, solve all the equations for premixed flames. Now, this is a simple solution because it's for simplified heat release. You can do it also for all kinds of heat release, and the expression remains the same, almost similar. You always find that the flame speed changes like the square root of the diffusivity multiplied by the pre-exponential constant, and you will see that this is an important statement. So let me summarize what you learn when you do that. So you learn that in a flame, there is a thickness, and this thickness is of the order of D divided by SL. You can write it in a different way, actually. You can say that the flame thickness multiplied by the flame speed divided by the diffusivity of the fresh gases is unity. In other words, the Reynolds number of the flame is 1. You know that you have the same relation for a shock wave. In a shock wave, the shock thickness multiplied by the shock speed divided by the diffusivity is 1, 2. And so that's a useful way to remember this expression for the flame thickness. Now, I've done one case. If you do other cases, the case I've done is this one, Echeki here. If you assume the reaction rate is written by this expression, this is what you find for the flame speed. But there are many other formula. If you want to keep the full formula, well, this is what you will get. In all the expression, whatever you do here, you will always end up with something which is the square root of the diffusivity multiplied by the pre-exponential constant. This is always the case. In the book, you will find also the full expression, but for the moment, I don't need it. What I need you to look at is this expression now. The flame speed is the ratio of the diffusivity multiplied by kinetics to the 1/2. This looks like a detail, but it's like we've built a large part of the second flame model on this property. What does this thing say? It says, well, for example, if you multiply the kinetics constant by 4, the flame speed will increase by 2. Yeah.
So can we use the same theory for detonation also with the shock and
Well, I'm going to say that in a second, yeah. That's the question, actually. The first thing you see in this expression is that the flame speed exists because you have heat release, well, you have reaction, that makes sense, but also because you have diffusion. If you don't have diffusion, the flame will not exist. So there is no premixed flame if there is no diffusion. That's specific of premixed laminar flames. If you do detonation, if you write the speed of a detonation, there is no diffusion. So for detonation, you don't care about diffusion. Diffusion is not important. For a premixed flame, diffusion is essential. No diffusion, no flame. That also tells you a lot of things about the step I mentioned yesterday, going from kinetic schemes to flames. The people working on kinetic schemes, and we'll hear about kinetics in a minute, they work on this here. They give you all the details on this term. This they don't care about because they don't have transport. They just look at autoignition times in an homogeneous box. There is no gradient of nothing. But if you get information from a kinetics expert about the kinetics, and you want to do a flame, then you need to describe this quantity. Of course, here, it's a very simple model, so there is only one diffusion coefficient. But in the real world, all the diffusion coefficient of all the species are going to be critical in your flame computation. And now, if someone gives you a scheme with 2,000 species and tell you, I've done everything, you got all the reactions, well, you have to tell him, okay, what about the diffusivity, the mass diffusivity of this very nice intermediate species that you've put there? He has no idea. Well, it's not his job, but it becomes your job now, because if you want to run a premixed laminar flame code, you need to specify the diffusivity, the mass diffusivity of all species. And for many species, we just have no idea. No idea what we should use. So that, by the way, tells you that going from kinetics to flames is a big step. And the big step is diffusion. Molecular diffusion must be done with precision. So it's also, the mechanism here is also somehow interesting to illustrate in a different way. Why does the laminar premix flame move? That's an interesting statement, actually. If you look at the flame at a given time, you see that if this is the temperature profile, you can basically split these two operators, diffusion and reaction. So the thing which happens if you look at a given time here and you try to worry about what's going to happen because of diffusion, you see that diffusion here will basically take heat from the hot zone and heat up here the fresh gases. Now, because these fresh gases are a little bit warmer, there's a zone here which is suddenly getting to a temperature which is high enough for reaction to begin. So combustion will begin now in this small zone and will bring this profile which has diffused to here, it will bring it up here, and you look at the red line, now it's the same as this one, but it has moved a little bit. And you see that this propagation of the flame is essentially a two-step mechanism. You need first to diffuse the heat, and then you need to react it. The other way to say the same thing is that if the flame is here, and I am a premixed element, it's a strange life which I have, because I'm cold. I feel, hey, nothing can happen to me, I'm cold. I cannot burn. And then when you come closer to the flame, you see, I'm getting warmer, but I'm still cold enough, And you see your friends on top of the mountain here, which these guys are hot, and they're sending you heat all the time. So the more you get up, you get warmer and warmer, and suddenly you're warm enough, and boom, then you react. But you need this diffusion to be able to take you up so that you can burn, because if you're cold, you cannot burn. We said that many times. Too cold, you cannot burn. So the mechanism is really a combination of the diffusion in this direction so that you can actually come back later and burn. So it's not a simple mechanism. So a useful feature of this equation, and that's the one we use for turbulent combustion quite often, is to say that if you look at this expression, you could multiply the diffusivity by a factor f and divide the kinetics by a factor f, and you will still have the same velocity. Right? That's obvious. Because in that case, the flame speed would be Fd multiplied by R over F to the half. That's still the same quantity. But if you do that, if you multiply the diffusivity by F and you divide the reaction rate by F, then the flame thickness here, which is d over SL, will become Fd over SL. So the thickness will be more. So that gives you a useful property, which was actually proposed a long time ago, again by this guy, O'Rourke. O'Rourke was really a genius, and he didn't have a big computer at that time, but he said, well, if I take my original equation for a flame, and I multiply d by f, and I divide the pre-exponential constant by f, I will have the same flame speed. It will propagate at the same speed, but it will be much thicker. So why is it important? Well, it's very important for someone who is writing a code. This is an example of a flame which is not thickened, and this is the same flame after thickening by a factor of 20. So obviously, if you want to resolve this flame, you need a lot of points. If you want to resolve that one, it's much easier. You need much less resolution. So we're going to use that for the second flame model because it's a way to propagate an interface, to propagate a flame actually, at the right speed, but with less points. So I would say in the physical world, it has absolutely no interest. It's only interesting for CFD guys, because in the CFD world, if you can save 20 to the cube points, of course, it's pleasant. Okay? So we'll go back to that. This is the temperature field, but of course, if you look at the heat release field, you realize that this is the unsecond release field, this is the second release field, and you see, of course, it's going to be much easier to mesh that one than this one. And of course, the nice thing about this problem is that you can adapt it to any mesh. If the mesh is fine, then you can thicken only by a factor of 5. If you have many points, you don't even have to thicken. If you have a coarse mesh, then you thicken by a factor of 100. Why not? I mean, for the moment, at that point, for the flame, it won't make a difference. The flame will move at the same speed. So that's a big advantage. Okay, let's continue mixing things a little bit here. Yeah.
In the second film model, like if you are hitting a flame a lot, say by a large factor, won't you change the velocity flow field or turbulence flow field, but the flame will actually see and what a thickened flame will see.
Sure, sure. This is what I will discuss this afternoon. The secant flame model, of course, has limitations. When the flame is very thin, or if it gets very large, it does not respond to the flow in the same way. It does not respond to stretch and to curvature in the same way, so we'll have to do corrections. But for the 1D laminar premix flame, it's exactly the same. Okay? But when we go to the turbulent case, there will be a price to pay. I mean, there is no free lunch, okay? We need to compensate. We'll do that this afternoon. Now, we need to talk about speeds again. Since I started talking about speed, I told you it's the flame speed, and I give you one number, but everyone knows that a speed is a vector, not a number, not a scalar. So if you talk about speed, we should talk about speeds because there are many of them. That's the first problem. We need to talk about vectors. The other problem is that we have to define different speeds. The absolute speed, the displacement speed, and the consumption speed. So I'm going to introduce them slowly, and you will see that this is an interesting business. So the first thing to say is that a flame is like a boat on a river. Okay? If you see a boat on a river and the boat is moving at a certain speed, you know it's not the boat speed. It's the boat speed plus the river speed. So it's the same for us. The flow is moving at a velocity u, and the flame is moving. If you look at the point on the flame, you see it moving at a velocity w, which are not equal. And the speed of the flame, that means the speed relative to the flow, is going to be w minus u. This is what the flame is really doing on its own. If the flame would be just convected, w would be equal to u. The flame just has to let it go. If the flame moves, it's really because there's a difference between these two quantities. So we have to be able to define that. It's not that simple because we're talking not about points but about surfaces. You see, when you see a flame surface at one point here, one instant, and then the same surface a little bit later, you have to define a speed, and the speed in this direction doesn't mean anything. So you have to define things according to the normal to the surface. So a right way to do that is to say, for example, that if a flame surface is here and it moves to here, its absolute speed is w dot n. Okay? N is the normal to the flame front. W is the flame movement, the flame speed that you would measure. When you say absolute speed, you have to define the reference frame when you do that. So it's really, for example, in the lab, and you ignite a flame here, the absolute speed is the speed of that point. Okay? It's really the speed at which you see the flame moving. And it's not necessarily the flame speed. That's where things get complicated. It's the absolute flame speed. We'll see later what that really means. If you want to see what the flame itself is doing, how it's progressing on the flow, you have to subtract the flow velocity. So it's w minus u dot n, which really means that the displacement speed is equal to the absolute speed minus u dot n. Now, this question of the absolute speed can be addressed in different ways. In a laboratory, it's an easy thing to do normally. If you have, for example, a spherical flame, you see it growing, you just measure the position of the flame front, and that gives you SA. If you are using code, in a simulation code, it's actually something you can back up directly from this expression, 1 over the gradient of theta multiplied by the derivative of theta, which you can directly get all the terms in the code. So in a numerical code, you can construct this thing directly from the different terms of the conservation equation.
How the flame front is defined actually?
Oh, okay. The flame front. That's if you do a spherical flame, everyone sees what the flame is. It's the place where you see the flame. In practice, we know that a lot of people like to define flames saying they are infinitely thin, in which case there is no problem. It's this point. In practice, we know they are not thin. So then things are going to be complicated. Even defining where you're measuring the speed is going to be an issue. I'm going to talk about it in a second. So let me go to the displacement speed now. The displacement speed, you have to subtract the flow velocity to the flame velocity. That's much more difficult to do experimentally. Some people do it today experimentally. You can track, you have to track at the same time the interface position by using, for example, drops which evaporate at the flame front. And at the same time, you have to measure, and at the same point, you have to measure the flow velocity. And you do the difference between two large numbers, and that gives you the displacement speed. The displacement speed can be obtained in a code quite easily because it's basically this expression which is all the right-hand side terms. So in a code, getting the displacement speed is actually easy. In an experiment, it's quite difficult. So, if you talk about a flame which is steady, we know that the mass flow rate is constant, so we know that the velocity is changing at every point. So the velocity is actually changing like the ratio of densities, which is the ratio of temperatures, because here, remember, there's no detonation, pressure is constant. So the flow velocity is actually increasing in the flame. So if you enter the flame at the flame speed, then you accelerate, and you will go up to SL multiplied by T over T1. So the flow is accelerating. And this is where things get tricky. Because if the flow is accelerating, we have to worry about what the flame is doing here, because the flow itself is accelerating. Then it gets different from the analogy I gave you on a river. On a river, the river flow is not affected by the boat on it. Here, the flame pushes the gases away behind them, and that's going to be a trick. Now, which really means that whether you talk about the displacement or the absolute speed, that depend on the point where you want to measure them. Normally, you want to define speeds by saying it's the speed of an ISO something. For example, you say it's an ISO temperature. You say, I take temperature, ISO temperature 2000 K, and that's what I'm tracking. If you're doing an experiment, you can put drops here. And if you put drops, you know, they evaporate at this temperature. So what you're looking at is the ISO, whatever temperature you get evaporation. If you're doing Schlieren visualization, you know that in the Schlieren visualization, what you really visualize is the gradient of temperature, the gradient of density. So probably what you're tracking is the maximum gradient position. But that's tricky. It would not be a problem if the result would not depend on the point where you measure it, but it does, as you will see in a second. And that's a problem which really comes from the fact that you have heat release. If it would be constant density, there would not be a problem. So let me give you an example. Well, a few examples, actually. The first thing is, and then this is where things get tricky. Follow me slowly. The absolute speed in a flame, like this one, must be the same for all the values of temperature. Why? For example, the 400K here line and the 2000K line must propagate at the same speed, because otherwise the flame thickness would change. So the absolute speed is a constant in most flames, right? Otherwise the flame thickness would change. So if the absolute speed here is the same, you can measure the speed of this line or the speed of that line, you will get the same thing. But if the absolute speed is the same everywhere, since the flow speed is not the same, then the displacement speed is not the same, and then things get complicated. So we're going to plot that in a second. Let's do, for example, a flame which is fixed in the reference frame where we are computing it. So this is how it would look. The flow will enter at the flame speed and will accelerate. Now, the trick is that since all the interfaces here, all the ISO lines are moving at the same absolute speed, then the displacement speed, which is the difference between these two things, this is constant, this is changing, so the displacement speed will change. And the displacement speed in all premixed flames is a very strong function of temperature. In other words, depending on where you measure the displacement speed, you're going to have a different result. And so, to say it in a different way, the displacement speed depends on the ISO contour you use to measure it. If you measure the displacement speed here, on the cold side, you will have a different value compared to a measurement done in the burn side. And that explains a lot of the problems we have when we start talking about displacement speeds in this community. This is why I'd rather work with another speed which is called the consumption speed. The consumption speed is defined in a completely different way. You take this equation, as I've done before, you integrate it from one side to the other, and you end up with an expression like that one, or basically you end up with an expression like this one. The flame speed is equal to 1 over rho yf1 integral of omega dot f dn. And you can do that with heat release or with any species. So the consumption speed is actually a measure of the integrated reaction rate in the flame. And this one is not dependent of the place where you measure it, of course, because it's just integrated over the whole domain. And the consumption speed has really many nice properties. The first property is the one I've mentioned before. If you multiply the consumption speed by rho and y, this gives you the fuel of flux entering to the flame, and that measures directly the reaction rate in the flame. And you will see for turbulent combustion that this is a useful property. What we really want in turbulent combustion is to know how much we burn, and this expression will give us this result. Now, you can actually view the consumption speed as a very useful concept here, which is to say a flame is like a membrane, and the flux through this membrane is controlled by the consumption speed. So you imagine if you have a flame somewhere, you can say that it's not a zero flux, okay? The flux is ρ1 SC. That's the total flux which goes through my flame at each point. So that the total flux is ρ1 SC. So the total flux of fuel is ρ1 SC yf1. That's the total amount of flux entering, of fuel entering here the domain. And on the other side of the flame, if you want to look, for example, at the flux of CO2 coming out of the flame, it's going to be ρ1 SC yf CO2 in the burn gases. And be careful, it's not ρ2, huh? It's ρ1. Even so, you are on the burn gas side. The flow rate is constant. It's ρ1 SC everywhere. And that's a very useful property that we're going to use many times now, just to view the flame as a membrane with an imposed flux. Now, let's go to a multidimensional extension that we will use for turbulent flames. Now, if the flame has a total surface sigma, if this is not a laminar flame but a turbulent flame, which is like this, if we know the surface sigma, and if we have some estimation of the consumption speed along this surface, SC, then the total reaction rate of this domain will be SC ρ1 yf, that's the fuel of flux per square meter multiplied by the surface. And this is the basic of flamelet models that we will describe probably this afternoon. And that's a good way to quantify unsteady turbulent combustion. We'll use this afternoon. So just to go back again, because there are people, for example, in this room, I don't know if India is working on the G equation. The G equation is one concept for turbulent combustion. The G equation works with displacement speeds. Flamelet model works with the consumption speed. Those are completely different concepts because, as I said, consumption speed is a measure of the reaction rate. The displacement, like the absolute speed, they are kinematic concepts. They tell you how the flame is moving compared to the flow. So if you do a flame like this one, that's a DNS, and you want to post-process this flow, and someone tells you, I want speeds. Okay, well, which speed? If someone tells you, I want the flame speed, you have to tell him which flame speed. If you want the consumption speed, you can go on each point of the surface, and we started doing that probably 30 years ago. That's not simple because, for example, here you might have problems not to confuse the two flame fronts, but let's keep it simple. We cut here, we integrate the reaction rate from that side to that side. We get one consumption speed. We go to the next point, we get another one. And then we can have statistics of consumption speed all over this line. And we can do correlations of the consumption speed as a function of curvature, stretch, whatever. I'll go back to stretch in a minute. But if you want to talk about displacement speed, then it's more complicated. Because if you want a displacement speed here, you know that the displacement speed here is not the same as the one here, and it's not the same as this one. Because they depend on where you are in the flame. And so there will be a displacement speed here, and there will be a displacement speed there, and there will be displacement speed all over the zone here. So now you have to condition displacement speed by the point where you measure it. And also, in general, the displacement speed in the burn gases doesn't mean much. What you really want is the displacement speed just ahead of the flame front. And that's the source of a lot of problems here. So let me give you a few examples. I will not go through the last two. I just want to talk about the first two here. I'm going to take a case where a flame is first in a fixed frame of reference. So typically, I'm sitting here and the flame comes towards me. So the flame is moving, in that case, in my reference frame. And I will do the frame in its own frame of reference and gives you all the speed. I'm going to assume, to do this exercise, that for all this flame, the consumption speed is the same. That means the flame is always burning in the same way. It's the same flame anyway. I'm just changing the frame of reference, but the consumption speed is the same. The kinetics are the same. Nothing is changing. It's just that I want to show you that the displacement speeds are going to be tricky. So let's start with the simplest one. So this is a wall. It's me here. There's a flame there, and the flame goes towards me. And the flame is moving at a fixed, at a fixed speed for the moment, and I know the consumption speed. I know SC. I want to know the flame position. I want to know the flow speed now. How do I do that? Well, you can take the conservation equation for YF here, and you just integrate it from 0 to xb, where xb is this point here. So what does that give you? Well, this gives you the mass of fuel which is left in this box. This gives you fluxes. This gives you diffusion fluxes, and this gives you the integral of the reaction rate. The integral of the reaction rate is the flame speed, the consumption speed. So this I know. These two things here, this is 0 because there is no gradient here and no gradient there. And this thing is 0 for another reason. It's 0 because there is no fuel here on that side. And it's 0 on this side because it's a wall. Okay? So I'm left with this thing equal to that thing, which tells you that dxf dt equals minus SC. And at that point, I see a lot of students telling me, hey, if it's just to write that, you know, that's too simple. But wait 5 minutes. That just says something obvious. If the flame speed is SC, this point moves at minus SC in my domain. Simple, for the moment. What is the flow speed? That's a more interesting question now. Here we have a wall. Here we have fresh gases. So these gases cannot move. We have no compression. So these gases are stopped. So the velocity is 0 from here to the flame front. They cannot go anywhere. What's the speed on the other side here? Well, you can write a simple conservation equation saying that the total mass in this domain can change only because of the gases going out. Okay? So dm dt has to be equal to minus ρ2u, because here this is ρ2, that's the density of the burn gases, and they are evacuated by the right-hand side. And what is m? Well, m is ρ1 xf for the fresh gases, and ρ2 xb minus xf here. xb is a constant that you can put, you know, where you want on the right-hand side. And you combine these two things, and you find that the velocity here is ρ1 over ρ2 minus 1 multiplied by SC. Okay, so the flow here in the burn gases is going away at a speed which is, you know, this is 7. So this is 6 or 7 times the flame speed. So the flame is moving at 50 centimeters per second, and the gas are moving away. The gas is moving away at 3.5 meters per second. Okay, now if you want to obtain from that the absolute speed, it's easy. It's the speed of the flame normalized along the normal. So here it will be equal to SC. So the displacement, the absolute speed of the flame is equal to SC. And now the displacement speed, this is where things get funny. If you combine all that, you find that the displacement speed is ρ1 over ρ divided by SC, and ρ is the density where you measure the displacement speed. So if you measure the displacement speed very close in the fresh gases, this is unity, and you find the displacement speed equal to SC. If you measure the displacement speed in the burn gases, there will be a factor, a mismatch of 6 or 7. So you have to measure it really on the fresh gases side. So when you plot all these things, that's the result. That's the distance to the wall. that's the absolute speed of the ISO level, which is constant. It's a flame which is moving without deformation, so all the values of the absolute speed must be the same. The flow velocity itself accelerates. The flow velocity increases so that the displacement speed is plotted here. The displacement speed is equal to the flame speed only in this zone here, and then right away it picks up and it goes to very large values. So if you measure the displacement speed of that point, you have nothing of interest, okay? And to see also the very large variation of the displacement speed. Normally, you should measure the displacement speed here, but the problem is that here, there is no gradient left, so there's nothing to measure. So it's really difficult to pick up the right displacement speed here. So let me do now the second example, where now we take a flame, and the flame is fixed, and we are in the frame of reference of the flame. So in that case, the absolute speed is easy. It's 0, okay? The flame is not moving, so its absolute speed is 0, so that's fine. You know SA is equal to 0. If you have that, the flow speed is easy to find because we know that's continuity of the velocity, so the velocity changes like this. It's ρ1 over u multiplied by the flame speed, and it's changing. And the displacement speed, again, has the same expression. You combine SA and u, and you find that SD is ρ1 over ρ multiplied by SC. And again, you see that the displacement speed is not a constant. It's not equal to the flame speed. It's only equal to the flame speed if you are very close to the fresh gases. And if you plot all these things, this is what you obtain. Absolute speed is 0. Displacement speed and flow velocity are equal. Okay, I'm going to jump the next two because I think you have probably understood the principle here. The thing I would like to note is that right away, there are complications here in this business. We see that there's an acceleration in this flow. The flow velocity increases far away from the flame. That will be a problem when we start talking about turbulent combustion because that will create turbulence. I'll come back to this later. That's the mechanism we already described. You know, that's the fact that the flame accelerates if it meets obstacles. And this is due to this effect, which I've plotted here again. If you want to ignite a flame, depending on where you put the wall compared to the flame position, you will have different results. If you put an ignition where you put the wall here and the cold gases here, the burn gases here, then this thing will accelerate a lot. And that's the reason why you will have possibly detonations. If you do it the other way, it's much better. If you put the wall on that side and you have the fresh gases here, they don't move, you're only blowing away the burn gases, and that will be much more reasonable. This is something I will discuss tomorrow probably, but this is an example of what's happening in a simulation of that type. There's a small flame starting here and pushing the fresh gases away. You can see it when this flame goes. This is an obstacle. You will see here the flow starting behind these obstacles. And that's a flow which is induced by the flame. And when the flame will reach this zone, it will accelerate even more, push more turbulence, and then this flame will accelerate. And the trick in this simulation is that long before the flame reaches that point has already started moving because of this blast effect, the fact that the flame is pushing away the fresh gases. And that's very important, as you will see later in the talk, because it's actually accelerating the flame without any turbulent combustion mechanism. The flame is creating its own turbulence and leads to this kind of behavior. So to conclude on these flame speeds, in general, the absolute speed itself, you don't use it because it depends on the reference frame. The consumption speed is the one you want to use. The displacement speed, I would say it's a difficult quantity. I would suggest that we work with the consumption speed as much as we can. So if I still have 5 minutes, I will finish with a few disturbing examples. There are disturbing examples for flame speeds. I'm going to give you a few of them. The first one is this one. If you take a flame stabilized behind an obstacle, like a Bunsen flame, for example. If you take the Bunsen flame, which is like this, you look at the flame here. This is what I've plotted here. This flame does not move. Okay. So you could say, well, it does not move, so does that say it has a zero velocity? No, because if you look at the particles, if you could see the particles on this flame, they're actually moving. They're just moving along the flame. That really means W is not zero, it means W dot N is zero. That's how you would actually find the flame position. It's the position where if you're sitting on the flame, you're traveling exactly along the flame. So you can use this expression, W dot N equals zero, to compute the angle of the flame, and you find something which is quite obvious, that the sinus of the angle here is the ratio of the flame speed divided by the flow speed. So if you're blowing slowly, the flame comes here. If you're blowing hard, the flame will lie along this axis. Okay? The stagnation point flame is another funny one. You know, stagnation point flames are very used in this community. How do we use them? Well, we have fresh gases going from one side, burnt gases going from the other side, and we blow them against each other. Looks like a strange configuration, but it works really well. And again, the flame here looks like it's not moving, but it is actually moving. The points, if you take 2 points on this flame front, and you could track them, you cannot do that because it's difficult to distinguish them, but if you would track them, you would see that they get apart from each other. Okay? So they are somehow moving. And you will see that this property of movement is related to stretch, and we'll need to talk about stretch pretty soon. Now the flame tip is another example here at this point, which is a funny example. Actually, we worked on it with Etcheki also 20 years ago, and Etcheki said that that's something strange here. If you travel on the axis of a Bunsen flame, this point here seems to be moving at a very high speed, because here we have maybe 10 meters per second. So is it possible that this point has a flame speed of 10 meters per second? That seems too high. So we did a simulation actually, and when we look, this is an isocontour of reaction rate. So this is where combustion takes place, and you see that for this flame, which is at Lewis equal unity, there is absolutely no difference between the side of the flame and the tip of the flame. So the consumption speed is the same everywhere, no difference. But the displacement speed on this point here is like 10 times more. And again, it shows that displacement speeds are complicated. So what's really happening here is the fact that the fuel is actually diffusing away from the tip so that there is much less fuel left here. And that's a complex example, but it really tells you again that consumption speed is easy to understand. Displacement speed is strange. 10 times the flame speed here doesn't make sense. So a last disturbing example, if you compute consumption speeds in a DNS, typically, you will find that you have one, which would be the unstretched laminar flame speed, 40 centimeters per second, for example, for methane. And you can have a little bit more. I will tell you why in a second. And if you quench the flame, you can have zero. That makes sense. Okay? If you have no combustion, consumption speed goes to zero. If you measure the displacement speed, I'm afraid that things get a little bit more complicated. Displacement speeds can take extreme values, and more disturbingly, they can take negative values. So negative values of displacement speed were discussed 20 years ago, and when we were doing the first DNS, people said, hey, it's stupid, but I will show you how this happens, actually. Let me first describe the large values of the displacement speeds. Why do you have very large values here? I've just shown you the flame tip of the Bunsen burner, which has a very large displacement speed, and the classical example in combustion is this one. If you have burn gases and you have a finger like that one, when this point will move here, even if these 2 points are moving at the flame speed, this one will be moving much faster, just because of geometry. You know, it will be crushed between the 2 fronts. So the velocity of that point can be extremely large. And this corresponds to the very large values that we find in displacement speeds here. We can have 10 times, 20 times the flame speed for a displacement speed, and that's only because of geometry like this, because of cusps. So that's for the large values. What about the negative values? The negative values are more fun. If you take a flame front which does not have a constant thickness, because something is happening in the flame front, you know, some chemical effects, for example, that really means that the point here could go that way, have a positive displacement speed because it's catching up on the flow. But a point like this one, the isocontour of temperature, if you have local quenching, for example, might go down. So this point would apparently go, you know, not against the flow, but in the same direction. So that would correspond to a negative displacement speed. Instead of moving forward and eating the fresh gases, it would be pushed away by the fresh gases. And if you do a DNS, that's an example of old, well, it's not that old actually, or 96, it's reasonably old, of a flame where turbulence enters into the flame front, and you do a PDF of displacement speed, you find a lot of negative displacement speeds, and they correspond to these points where the flame fronts are actually getting broader than they should. Actually, this point here, that really means that a place like this, for example, is actually going away from the reaction zone. And again, you can do the DNS, but I'm not sure what you can do with them. Okay, you can plot a lot of things and white papers, but no one can use that afterwards. So my advice is really prefer to use the consumption speed. Okay, I will stop here and we'll continue this afternoon on this business. If you have any question, it's the right time. Yes?
So when we write the governing equations, all the equations were written in the laboratory frame of reference.
Yeah, sure.
But then in the continuity equation, we were switching the frame of reference from the.
We can do that if it's a constant velocity frame of reference. It's still valid. Okay, the equations are valid as long as the frame of reference moves at a constant speed. Newtonian approximation, it's the same equations.
So even the momentum equations.
Oh yeah, it's the same. As long as it's a constant speed. Okay. If the speed would be changing, then it wouldn't work. But if the speed is constant, we can work in any frame of reference. It's still the same equations. They are invariant.
And then this definition of flame speed, it actually comes from the study of 1D planar flames, right?
Yeah.
So how good it is to extend the same terminology to something a flame which is highly common? I think it's because of this reason I get all the negative and very highly values.
Even for a 1D flame, you can have strange displacement speeds. It's the same. Yeah. No, it would be the same. Even for 1D flame, you can have negative values of displacement speeds too, even in 1D. Of course, when it's curved and stretched, then anything can happen.
And then you were mentioning about the G equation.
Yeah.
So, but in the book it's written like there is an equation, then there's something like an interface, and then you track the interface
Yeah.
based on some equation.
Yeah.
But ideally, like, is there a possibility that you start with the governing equation, and from there you sort of track the flame interface and get this G equation?
Yeah, you can. You can start from the fuel equation. Actually, it's the same equation. Okay, it's the equation for the fuel is this one, and here it has a diffusion term and a reaction term. From there, you can go to the G equation, which is dg dt plus ui u grad g equal sd grad g, because basically this term comes here and these two terms get combined into that one. You have to approximate, if you say the flame is infinitely thin, etc., you can, these two terms together go into the displacement speed. And then you can just solve this equation. And the main problem with the G equation is really to handle the variable density. If you do a constant density flame, you're fine. The problem with the G equation is that if the density is changing, you are in trouble. There's a woe here, actually. And people who try to use the G equation, they always get into problems to reconstruct the density field. Because in the equations, it's easy to say that density is a step function. But as everyone knows in this room, if you do CFD, you cannot do that. You need to find a way to handle an infinity steep gradient, and that's difficult for density. That's the main problem.